It's the last day. So first, let me do what I promised yesterday, which is to give you a proof of this matching lemma, which is useful in several places. And then we will explore how all of the tools that we have put together so far will fit into some of the applications that we mentioned. So again, let's see this matching lemma. So let G be a bidirectional. And we assume that it is superregular. So let's say this beautiful notion of epsilon delta superregular. So again, this means G is epsilon regular in the regularity sense, and the minimum degree is at least delta n. So it's two vertex size of G equals by n. And you could think that delta is much bigger than epsilon. And our goal is to produce a probability distribution lambda on perfect matching of G. Such that we have the property that for every tuple of edges, E1, E2, up to ET. Sorry, this is not yeah, so for every tuple of T edges of the graph G, we have that the probability under this measure lambda that we produce some perfect matching M that contains all of these edges. Maybe I should write this, is at most some constant may depend on epsilon and delta dividing by n. Okay, so this is just to expand out what we usually just say that lambda is a p-spread big O of 1 over n spread distribution on perfect function. So let's prove this. So the way that we produce, so our goal is to produce a random matching. We can choose a distribution, but mainly we want to produce a random matching such that if we look at the matching that is outputted according to our procedure, it will satisfy this nice property that we want here. So let me tell you how we want to produce this random matching. So this is the procedure for it. So let's let A be a random subgraph of G. And this is how we sample this random subgraph of G. It will be somewhat different from the other sampling procedures that we have seen. So here, for each vertex B, we include a random collection of some number, let me call it C, just some big constant that may depend on epsilon and delta, edges around V. Okay, and that's exactly the distribution of this random subgraph, okay? So for every single vertex in this bipartite graph, we look at the vertex and then we pick C random edges adjacent to that vertex. And then we just take the union of all of the edges that we have picked and we say that that is this random subgraph, okay? So the main claim in the proof is to show that with high probability, this random subgraph K will have a perfect matching. So most of the proof will just be in the verification of this claim. And at the end, I'll tell you how we can quickly conclude a proof of the lemma from this claim. So, well, how can we prove this claim? I suggest this. Well, if we have some graph here, bipartite graph K, and we want to find a perfect matching. So all that we need to do is to check the Hall's condition in this graph K. Right? So let's do that. So let's, for example, consider some vertex subset A prime of A. And let's say that A prime has size equal to X. And let's consider some vertex subset B prime of B. And let's say that the size of B prime is exactly X minus 1. Okay. So a violation of the Hall's condition, so the Hall's condition being violated, means that there exists some X and A prime and B prime with these constraints, so that the neighborhood of the set A prime in the graph K lies entirely in the set B prime. Okay. And by symmetry, okay, so by symmetry of the two sides, continue the proof here, we can assume, let's say that X is at most half of the vertices on the left. Okay, so the other, if X is bigger than n over 2, then you can actually just look in the graph and you can say that if none of these events happen for X applied at most n over 2, then it will also cover for X bigger than n over 2. So that's a similar proof. So let's focus on this range. X is at most n over 2. We'll split the verification into two cases. Okay. In the first case, let's say that X is less than n over 2, but still somewhat big. So there's some parameter eta, depending on epsilon and delta appropriately. Think about it as a small constant. Let's first verify that Hall's condition cannot be violated for every set A prime of size at least eta n. Okay, so in this case, we will use the regularity assumption on the bipartite graph G. Right, so we have two sets here, A and B, and we have this subset A prime that still has a fairly large size, it's a constant fraction of A, and we have this just slightly smaller set B prime over here. So by the regularity assumption, well, we have this rather big, well, we have a linear size set B prime here. The number of vertices from A with the wrong degree to the set B prime will have to be small. And what in particular means a wrong degree, all but at most epsilon n vertices of A needs to have the property that they have something like, or one more notation. So let D be the density of the graph G, which is at least the minimum degree delta. Of course, so here minimum degree is delta n. So I normalize this is the normalized density. D is at least delta. So all but at most epsilon n vertices of A by regularity will need to have D plus minus epsilon times the size of B prime edges to B prime. Okay. So in particular, all but at most epsilon n vertices of this set A prime will have some well-controlled neighborhood inside the set B prime in the graph G. Okay. Okay, so now for each of these vertex, right, we are choosing, when we choose this subgraph K, for each of the vertices in A prime, and let's just restrict our attention to the guys that have the correct degree to the set B prime. For each of these, we are going to pick C edges at independently at random around the vertex. And in order for the neighborhood of A prime to lie entirely in the set B prime, we will need all C of these edges to have been chosen from this neighborhood. Right? So, okay, so do I need the first one? Yes, so maybe actually let me. So we had let me first actually apply a lemma that we proved yesterday, just to put myself in a more convenient assumption here. So by this lemma we have yesterday, we can actually pass to a subgraph of G. So we can assume without loss of generality that actually G is epsilon superregular with density B. And this in particular means just that the degree of every vertex in G is already controlled. It's between D and D plus epsilon times n and D minus epsilon times n. So the degree in G of every vertex is between D plus minus epsilon. Okay. So by the lemma yesterday, we can pass to a spanning subgraph of G with this property, and so we can actually just assume without loss of generality that we already have it.
Sorry, then this D is it the same with the density of G?
Yeah, it's that D is exactly the same as this D. So we can forget this now. So you can assume that G is already processed so that if D is the density of it, then it is now epsilon regular, and also the degree of every vertex is around D times n. And we saw yesterday that we can do this. Okay, so now we can control the probability of this event, right? So the probability that the neighborhood in this random subgraph K of A prime lies entirely in B prime. Well, when this event happens, then for every of these single vertices, its degree in G is something like D times n up to an epsilon. And all of the C edges that we pick around this vertex must have come from its neighborhood into B prime, which has size only D plus minus epsilon times the size of B prime. So this probability in particular is at most, well, for each of these vertex, the event that we care about, it has probability something like the degree of the vertex, which is D minus epsilon, which is at least D minus epsilon times n. And then into B prime, its degree is at most D plus epsilon times the size of B prime. And this, because we have C edges that we are going to pick independently at random, for each vertex, the probability that its neighborhood lies in B prime is at most this raised to the C. And then the number of vertices that we have is at least the size of A prime minus epsilon n. So we can control the probability of this bad event by this quantity here. So now in particular, this is at most or something like D plus epsilon over D minus epsilon times x over n to the power x minus epsilon n times c. And c is a big constant depending on epsilon and delta that we can choose later. So we can do some simple estimates to simplify this tailbow that we have currently. So this is at most, let's say, x over n plus epsilon over d raised to the power of c, x minus epsilon. Okay, so in the end, we want the whole condition to hold for every set, A prime and B prime, right? So first, let's just fix x. Actually, just think that x is anything that goes in that range between eta n and n over 2. And now we are going to take the union bound over the two sets A prime and B prime. Okay, so look at now this probability that there exists A prime of size x B prime inside x minus 1, and the neighborhood of A prime is inside B prime. This is at most, well, the number of choices for A prime and B prime, we know, and choose x, and choose x minus 1. And then we have this tail probability, x over n plus epsilon over d, we can see x minus epsilon. Okay, again, we need to do some estimates. So let's bound this by e squared, n squared over x squared. Maybe you can also make e any larger constant, it's inconsequential. And then in the rest of it, we have, oh, this is raised to the power x. And then we have x over n plus epsilon over d, we will see x minus epsilon. Anyway, because x is fairly large compared to epsilon n, if you choose eta appropriately, eta is bigger than 2 epsilon, say, you can make sure that this constant, that x minus epsilon n is still at least x over 2. Okay, and if you do that, then this we can bound by e squared, n squared over x squared. We have then x over n plus epsilon over d to the power c over 2, all raised to the power x. Okay, so, well, x over n plus epsilon over d is almost just like x over n. So you can now just observe that that quantity we have over there, we will be able to bound it above by maybe some other constant times x over n plus epsilon over d to the power c over 2 minus 2, and then raised to the power x. So in our range of parameter, this x over n plus epsilon over d is at most 2/3, right? And then we can pick this constant c to be very large. So definitely we can make this less than anything that we want. So maybe 4 to the minus x is fine. Okay. That's the first range of parameter. Now let's consider the other case. Where the size of A is very small. So in this case, we are going to use the minimum degree condition that we have in the graph G. Right? So every vertex in A will need to have degree at least around d times n. And the size of B prime, which is x minus 1, is in particular smaller than eta n, so much smaller than the minimum degree of a vertex. So now we can just bound directly the probability that the neighborhood of A prime fits inside B prime. This is at most, well, again, for every vertex in A prime, the number of options it has is around d times n, that's its degree in a graph G. And then if the neighborhood of that vertex in the end lies inside B prime, then all of the C independent options that we choose have to come from B prime. So we can bound for each single vertex that probability by, let's say, x minus 1 over d minus epsilon times n raised to the power c. And again, we can raise this to the power x, which is the total number of vertices that we have in A prime. So again, we do the union bound. And we get that quantity Now we are looking in the range where X is small. But still, in this range, we can estimate this. Okay, pretty much the same way that we estimated before. So we look at something like E. That'll be a bit quicker with the intermediate estimation here. Where we get some excessive quantity like this. So, okay, if we now just combine the bound from the two cases, then we observe that the probability to conclude the probability that K fails the whole condition is at most what we have over there, so the sum over all of the large X, 4 to the minus X, plus the sum over the small x, this probability here. And one can check that this probability is, if one chooses the constant C appropriately. Okay, so up to this point, we know that with high probability, this random graph K will contain a perfect matching. So once we know that, then we can finish the proof of the lemma. Okay, so now what will we do? When K has a perfect matching, we just actually output if an arbitrary perfect matching of K. Let's call that M. Because K is random, this perfect matching that we output M will also be random. So let's let lambda be the distribution of the output M. Okay, so now M will be a random perfect matching in G. So all that we need to do is now to verify the spread property for this perfect matching M that we output. Okay. But we can check that directly. So let's fix any T edges, E1 up to ET, that you want. And let's look at the probability that M contains the edges E1 up to ET. Well, if M contains the edges E1 up to ET, then first, the random graph K have to contain these edges. Okay, but now let's look at how we generated this random graph K. Out of every vertex, we pick C random edges. Okay, so what's the probability that E1 is contained in K? E1 has two sources of becoming an edge in K, right? There are two vertices incident to the edge E1. And if E1 lands in K, then in the C edges adjacent to one of the two vertices at the endpoint of E1, we must have picked this edge E1 to be in the graph. But the probability that that occurs is at most C over N. So it's at most 1 over N for each single choice that we make, and we have C total choices. So from each vertex, the probability that E1 is one of the options that that vertex choose is going to be C over N. And there are two endpoints, so perhaps we can up about it by 2C over N. And then this is going to be independent across these T edges. So we can up about this probability that the random graph K contains the T edges by this quantity here. Okay, and that's exactly what we want.
Is it okay to not conditioning on the K contains a perfect matching?
Yeah, you're right. So you need to condition on K containing a perfect matching. So here we will divide by the probability that K contains a perfect match. So 1 minus the probability that K has no perfect match. Anyway, that's from 1 plus 0, 1. Indeed, one need to put that back. Okay. Any question about this demo? Well, in fact, in many cases, many of the applications where we need to construct a spread distribution, then it's usually constructed in a somewhat algorithmic way, like what we are doing here. So we just kind of create a randomized algorithm, so a randomized natural procedure that will construct what we want to find. And then we just define the distribution to be whatever distribution the output of that algorithm has. And usually the algorithm would come with kind of the spread property built into it. So for example, here, this random graph K that we construct is kind of constructed so that it automatically has the spread property. And the similar thing happens in many of the other applications. So given that we have proved this matching lemma, I want to mention next, maybe, a way that one can just directly build and iterate this matching lemma in order to obtain the corollaries, some of the corollaries that I mentioned regarding the clique factors in a graph with high minimum degree. So let's discuss that a little bit. So again, maybe let's say exactly what I'm going to prove. What I'm going to prove is that if you have an R-patite graph G between vertex sets V1 up to VR, let's say all equal sign. And let's say that every pair, the graph between every pair, GVIBJ, is epsilon superregular. So, okay, so what we want to now construct in this graph is the following information. So should we define this object, HG? This will be an R uniform hypergraph on the same vertex set. And the edges of this hypergraph are exactly just the R cliques in the graph G. R patite cliques in G. And the conclusion that we are going for is that there exists an big O of n to the 1 minus R spread distribution on perfect matchings of H. So first, as a corollary, so if you can construct a spread distribution, then it is actually very easy to translate that to the number of perfect matchings that HG contain. And in fact, perfect matchings in HG are exactly just the KR clique factors in this graph G. So this will then give us the correct count of KR factors of G up to this constant factor in the base of the exponent, but ignore that constant factor. So if you want sharp count, then the spread distribution would directly imply that. And so another corollary, of course, will we be able to get the conclusion about robust threshold. Okay, I'll say it this way. So if we sparsify this super regular R-type graph G, and the probability that we sparsify the edge is something like some constant log n to the 1 over R choose 2, n to the minus 2 over R, then this will contain still KR factor with high probability. And because this is the same order as the threshold in the, even if G was a complete graph, was this in type. So let me actually mention how in this case we can obtain this correct fractional power of log n, because if we just apply directly the Kahn-Kalai conjecture, then we will lose a log factor, not a log to the 1 over R choose 2. So that how that follows is a very nice result of Riordan, and then also later built on by Heckel. So they state that if you consider some R, let's say at least 3, and you consider some parameter P that is at most around n to the minus 2 over R plus some small constant depending on R, which, okay, our parameter is in that range, actually plus. Then we have the following guarantee. There exists some coupling of the random subgraph of the same graph G that we will look at here, the R-type graph G, and this hypergraph that we constructed out of the R-clicks in G, but now we sparsify by some probability pi, and the correspondence between P and pi is kind of the obvious one. So the probability that you see a click in the graph would be P to the R choose 2. So we take pi to be P to the R choose 2. And then, okay, so they show that there exists a way to couple this random subgraph of G and this random hypergraph of the click factors, this random hypergraph where we sparsify randomly the hyperedges corresponding to the clicks in G, such that it holds that for every edge in HG pi, the corresponding click must appear in GP. So once one has this result, it essentially allows us to move without any loss at all between the model where we look at the graph and we want to find the KR factors, and the hypergraph model where now instead of the factors we are trying to look for a perfect matching in the hypergraph. So this gives us a sharp translation between the two settings, and that's exactly how one would get this fractional power of log out of the result, because we will first just apply the Kahn-Kalai conjecture to the hypergraph setup. So we get that the threshold is of order log n times n to the 1 minus r, and then we pass through this coupling in order to recover the correct power. Okay, so with that, let me tell you a bit about how we can prove that lemma rho. There are also multiple ways to prove it, but this is one way, which is kind of just building on the matching lemma that we have already shown. So the key step there actually is the following kind of next step, which is also then the induction step for getting the higher uniformity. So let me first just consider the 3 uniform case. And consider this tripartite graph where every pair of parts is superregular with density D. So there's one small assumption. So let's assume that for every edge E, which is V2, V3, the number of vertices V1 such that V1 is adjacent to both V2 and V3 is at least kind of the right number. So D squared minus some small constant, let's say root epsilon, times n. Again, the 3 vertex parts have size n. Now, we consider a distribution lambda 1, which is an optimally spread distribution, say C over n spread distribution on perfect matchings of G between the 2 parts, V2 and V3. Okay. So we will construct now an auxiliary object. So in this picture, we have 3 parts, V1, V2, V3. We first look at the graph between V2 and V3, and then we choose out some random matching according to this C over n spread distribution. Now I will construct some auxiliary graph. So let's call this matching M1. So we'll now construct a bipartite graph, gamma M1, where the 2 vertex sets, where the vertex sets are between V1 and the edges in the matching M1. And in this graph, we will simply connect V1 to the edge E1 in M1 if, well, V1 is adjacent to both endpoints of E1. So in this graph here, if we have for each vertex in V1, if it is adjacent to both endpoints of the matching edge, then we will put in this graph gamma an edge between V1 and the vertex corresponding to the matching edge. Okay, so now this will be some bipartite graph, gamma n M1. It's a balanced bipartite graph. And what we will prove is that with high probability, actually with probability 1 minus something that is exponential in negative n, we will be able to obtain that this bipartite graph gamma M1 contains some very regular bipartite subgraph. And the parameter is a bit weird, but that's what we get out of the proof. So kind of the next step, and then it will be forming the basis for the induction step to go to the higher clique factor. So roughly how we build the clique factor is just to iterate this type of procedure, right? So in every step, we take a pair of parts, we sample a spread perfect matching on that pair of parts, and then roughly we replace that pair of parts now by a single part where each vertex in this new part corresponds to one matching edge. So then we have moved from uniformity R to uniformity R minus 1, and then we just continue this process. So in every step, we only need the tool, which is the construction of a spread perfect match. Okay, I will not maybe go into the full details of this, but just give some main ideas behind how this works. Maybe so, right. So how are we going to prove this? Well, we actually have to use the property that this random matching M1 is spread someplace. We can do the following. Let's check actually first that this graph gamma of M1 is with high probability eta regular for some small eta. And here the eta we will use is 1 over root log 1 over epsilon. Okay, so in particular, what do we need to do in order to check this? So for every vertex subset, let's fix some vertex subset S1 of V1. And let's say that we have that S1 has started with eta n. Sorry. Let's have this rho n, where rho is 4 eta, but ignore all of the changes between the small parameters inconsequential. So for the regularity, right, what we want is to be able to show that roughly for every linear size vertex subset of V1, if we look at now these matching edges in the random matching M1, then most of the edges in M1 need to have the correct degree into S1. That's roughly equivalent to the regularity property. So we want to show that most of the edges in M1 will have degree to S1, which is exactly what we want most. The correct degree turns out to be just around d squared. So let's say d squared plus minus eta times rho n into n. But in order to do this, we can just, well, first let's fix S1. Now, before sampling this matching, let's actually look at the graph between V2 and V3. We'll say that an edge E in this graph between V2 and V3 is bad if it has the wrong degree to S1. And by regularity, it's easy to show that the number of bad edges will have to be small. So it will have to be something like a delta fraction of the total number that we have. So it's defined. So let's say that E between V2 and V3 is bad if the number of vertices V1 in V1 such that V1 is adjacent to both endpoints of E. This is not in the desired range. And in fact, it's actually going to be useful to even define this bad property for each of the vertices in V2 and V3. So let's say that V2 is bad if the number, so this is not V1, S1. The vertices V1 in S1 such that V1 is adjacent to V2 is not within eta of B times rho n. Okay, so then we use regularity. The original assumption on the regularity of the tripartite graph to show that there are at most, we'll use epsilon n, bad vertices, and for each not bad vertex, so each good vertex, the number of bad edges adjacent to that vertex is at most epsilon n. So now we sample our random matching M1. And actually, in order to maintain, or in order to have this regular property of the bipartite graph gamma M1, all that we need to guarantee is that only at most a small something depending on eta, epsilon, and delta, fraction of the edges in M1 can be bad edges. And as long as we guarantee that almost all of the edges in M1 were coming from the good edges, then we are done. Okay. So that's some check that we can do. Claim is that so we want to guarantee that M1 has at most something like eta n bar edge. Let me just make sure that the constants are correct. Yeah. Okay. And the probability that M1 is bad is that it has more than eta n bad edges. This we can bound just using the spread property, right? So first we have a small number of ways to choose out this eta n number of bad matching edges, and then we're just going to do a union bound. So for each fixed choice of eta n bad edges, the probability that M1 contains them is at most C over n raised to the eta n. And we're just going to sum over all of the possible ways that we can choose these as eta n bad edges. And the bound will be something like this. So we first choose our location for the vertices in the bad edges. And then for each of these vertices, we're going to have epsilon n choices for the other endpoints. So for the rest of the vertices, of course, we don't have any constraints. So these are the ways that we can choose out these eta n bad edges. And then the probability that M1 contains them is at most C over n raised to the eta n. So actually how I do it here, I even sum over all of the ways to choose n edges so that there are at least eta n bad edges among them. So we'll have just this style in the end. And then calculation to see that this is small. So this is at most n times log 1 over epsilon roughly. So because of this very strong tail, of course, we can just now do the union bound over all of the subsets as well. Union bound over S. And we can check that once we do this union bound, so if this bad event doesn't happen for any S1, then this graph gamma M1 is something like that parameter over there, regular. Okay, so this is the harder half of the two properties that we need to guarantee, but we also need to guarantee that it has large minimum degree. But guaranteeing that gamma have large minimum degree, for one side, it just comes from this assumption right here. And for the other side is kind of a simpler estimate than the one that we are doing here for the regular property. So let me skip.
Did you write the purpose that in the condition of V2 being that is for the crossness delta will equal to
Sorry.
You wrote D plus delta, but did you write in focus on?
Yeah, B plus minus A. Yeah. Thank you. Okay, so as I mentioned before, then once you have this lemma, you can iterate this to obtain this lemma for the general R-click factor. Right? So for example, if you want to move to uniformity 4, then we first, between these two parts, pick out the perfect matching, replace it now by this new vertex part, and then run this tripartite argument between these two, this tripartite graph. Questions about big factors? Okay, so maybe next I will say a little bit about hypergraph perfect matching, so both the Dirac threshold, because then the technique is interesting for use iterative absorption. In fact, there's another proof for this result on clique factors, also using iterative absorption. But I presented this one, which is simpler. Maybe one remark I should also make is that, of course, this is kind of the key component that we want in the final result, right? That I stated the result that if we have just the correct minimum degree condition on the graph G, then we can already guarantee this robust threshold property. And if you want to prove that, then you first need to apply the regularity method in order to pass yourself to some super regular setting where you can apply this lemma. And then, of course, there's also this tricky part that if you apply the regularity method, then there will be some exceptional vertices. You have to redistribute them in the right way, and you have to separate out the critical cases and analyze the stability around these critical cases. So there are all of the usual work, but this work, in a sense, already happens in the previous extremal combinatorics proof. So already in the regularity method proof for the extremal result, all of that insights have already been needed there. So we just need to kind of go through them and see and guarantee that we can inject the correct amount of randomness to every step that we need. But in the end, then with all of that, the key would lie into this setup where we have the super regular graph. Okay, so with that, now let me tell you about hypergraph computations. So again, what is our setup? So let's consider K-uniform hypergraph. And we will define this parameter, delta LK, we roughly mentioned yesterday. This is going to be kind of the minimum L degree condition that we need in order to guarantee a perfect matching in a K-uniform hypergraph. So this T and LK dividing by and choose L. T and LK is the smallest D to guarantee that once the minimum L-tuple degree of the hypergraph H is at least D, then H is a perfect matching. So again, delta L of H just means delta L of a tuple of L vertices is just the number of hyperedges in H that sits on top of that set of L vertices, and delta L is the minimum over all L tuple of vertices of that L tuple degree. So then H has a perfect match. Okay, so in general, we don't know what the values of these delta LK are. That's the extremal combinatorics problem. But still, since we can prove the theorem that I stated yesterday, and this was independently in our work with Bartoli and Simkin, but also by Kahn-Kalai, Ostos, and Fenninger. And then there are also several later developments, several later proof techniques, for example, like Kelly, Bobrovsky, Uyesser, and use Lang, Tanhuizer, Matamala. So lots of different developments around these objects. But what do we want to prove? Here we want to prove that if a hypergraph H has large L-tuple degree, so here we want, for this result I state, that works for all L and K, one is some slack. So in at least delta LK plus some epsilon times n plus k minus L, where n is the number of vertices in the hypergraph. Then, even if we specify this hypergraph H by the correct threshold, so some constant log n to the 1 minus k, it will still have a perfect matching with high probability. Okay, so this is what we are going for now. And now what is our proof of this result? Again, we will, so again, our intermediate step would be to construct some spread measure over the perfect matchings in the hypergraph H. So there is this optimal spread distribution over the perfect matchings in H. Okay, so let's focus on this goal. So what we will do now for the construction of this perfect matching is what we would obtain again from the following random procedure. So in this procedure, we will create a shrinking sequence of random vertex subsets. Okay, so we start with the entire vertex set V, and then we sample a random vertex subset V1 of V, where each element is retained independently with some probability, something like epsilon squared. And then we just continue this process until we hit the last vertex part. Okay, so when we hit the last vertex part, this will already have quite small size. So these are the guarantee that we want for the vertex set. So first, all of the vertex sets will shrink at a rate of roughly epsilon squared. And if we sample randomly, then of course concentration would always allow this. Then we want to start when the last vertex set is already quite small. And for here, maybe something like then we want to maintain the L2 degree condition roughly in all of these vertex sets. Actually, the guarantee that we have will be a bit stronger. It looks like this. For every L2 of vertices S, if we look at the degree of S into the vertex sets Vi, so this just means the number of hyperedges in H that contains L vertices from S and the remaining K minus L vertices from Vi, then this is going to be at least still this parameter that we have originally times the size of Vi choose K minus. Okay, and we will just choose these vertex sets Vi completely at random, and by concentration, we'll be able to guarantee these properties if we just choose Vi plus 1 to be a random vertex subset of Vi with density roughly epsilon squared. So now you will use the following lemma. So for that. So yeah, okay. So first, maybe let me say the lemma in which we will use this for. So here, in every step, roughly we will repeat the following procedure. So let's say U is the vertex set in the next step, and this is the current vertex set. What we will do is that if we have the assumption that for all S of size L, the L degree of S into U is large, then there exists an optimally spread distribution. So again, n to the 1 minus k distribution on now matching, but not necessarily perfect yet, partial matchings, M, which has the property that it covers all vertices outside U, and it uses at most a small fraction of vertices in U.
You are want to use the iterative absorption.
Yeah, so this we are using iterative absorption. So these VIs are the vortices. And this is the partial matching lemma in every step. Okay, so we just do iterative absorption. So we start with the big vertex set. We then find actually some partial matching that covers most of the vertices outside U. And then for the few remaining vertices, we will cover it by using the vertices in U in some maximally random way. Then we have the remaining part of U, and then we just continue this process with respect to the smaller vertex sets. Okay, and once we do this till we hit the last vertex set VK, which is very small, we can guarantee that VK still have the correct minimum degree condition to guarantee a perfect matching, and it's automatically will have the correct size to contain the perfect matching. So then we just actually find an arbitrary perfect matching in the last part of the vortex, and we output everything together as the random perfect matching that we have, and that we will verify to have the correct spread property. So this partial matching lemma will be key in every step of this procedure. And so what we need to do for this, I'll just again roughly sketch the idea, is to do the following. So first, we will find some nearly regular subgraph on this hypergraph induced on H minus the vertex at U. Okay, so the tool for finding this nearly regular subgraph is the following lemma. So if we have high enough minimum degree to contain a perfect matching, then there will exist some subgraph with much nicer control on the maximum degree. So the subgraph will still be fairly dense, some constant fraction of the edges. And now we can guarantee that its max degree is at most, again, some small constant times what you expect. Okay, so roughly to do this, we kind of find an almost perfect matching in the hypergraph H with this minimum degree condition. And in order to find that almost perfect matching, we use some idea of Ferber and Tuan. But roughly the main idea is you take a random partition of the vertex set into small blocks, and then you can check that actually pretty big fraction, so almost all of the blocks will still have the right minimum degree condition to guarantee a perfect matching. So then you find the perfect matching in all of these small blocks, and the ones which you cannot find a perfect matching, you ignore. That will give you an almost perfect matching in the graph H. And then you just repeat the procedure. You show that you have the right conditions to just continue that procedure and extract out enough almost perfect matchings that allow you to get this more regular subgraph H prime of H. Okay. So once you find this type of a nearly regular subgraph of H, then you can actually find a nearly perfect matching in this random subgraph, in this subgraph H prime that has the correct spread property by first subsample again a subgraph of H prime with just the correct number of edges that you need to support a perfect matching. And then you use the Rodonipo for that very sparse subgraph in order to show that you can find an almost perfect matching in that subgraph of H prime. And again, because the almost perfect matching you find is confined within a random subgraph of H prime, it will automatically have the correct spread property. Okay, so it's roughly the main idea for proving this iterative matching lemma, which then you combine with these random vortices in order to find the spread perfect matching in the end.
Well, I may need something, but usually when we use the iterative absorption method, the final round of the vortex, we embed the exclusive absorber first and then make it complete. Then continue make it
So in this case, we don't actually need to do much. So, but when we arrive at the final vertex set, we actually just need to have the minimum degree condition in that vertex set. So we can guarantee that whatever we have left at the end, it has a sufficiently high minimum degree. That's not so hard to guarantee. And so we can just always find a perfect matching in the remaining vertices in that final field. So it's a simple application. Yeah.
There is a question in the chat. Why does the random block lemma not give the desired spread measure on the arclic complex HG?
So that was regarding the earlier applications, perhaps. This one. Yeah. So the only difference here is in the end, because I want to, well, the blow-up lemma applies to the graph. So anyway, in the blow-up, we can use the blow-up lemma to, for instance, find click factors. But exactly because of this fractional power on the log factor, I don't want to directly just construct the measure at the level of the graph. And so actually, yeah, but so the main difference here is that the spread property and the spread measure that we construct is going to live in this R uniform hypergraph, and the correct spread is at the level of the R uniform hypergraph. And that is needed just to recover the correct fractional power of the log factor, because then we use the coupling of Riordan and Heckel that I stated earlier. And really, that's the only reason why here we are proceeding through this different proof to construct the spread measure on the perfect matchings in the hypergraph and the direct application.
Is it because for hypergraph, the isolated vertex, the coupon collector obstruction log factor is different?
That's right, exactly. Well, in the hypergraph, the coupon collector would give you exactly a log factor that's off from the correct first moment, the expectation threshold. But when you go back to the graph, then the coupon collector is a bit different, and that log should come with a fractional power. Does that answer the question?
Yes. Yes.
See, right. Got to be a bit careful that actually the blow-up lemma in the graph does not say something directly, but we are leave that consideration to afterwards. Then I want to get to the last application I will discuss, which is now on the perturbed random graph model. Yeah, basically, maybe the vertex spreadness of the click factors that you obtain from the random blow-up lemma does give what we want here. Well, that complete. So for this last application, let's turn to the perturbed random graph. So now we'll now use the random blow-up lemma, but okay, we'll see there's a very small change of perspective, but it's somewhat interesting. So again, let's state what I will prove in the perturbed random graph model. So we'll prove that if we have a graph G with minimum degree is 1 over k plus 1 times n. But we need a little bit of a slack. Ideally, one should be able to, again, go through carefully the details in the regularity method and the stability around the extremal case in order to remove this additional epsilon. Then, if we look at the union of G and a random graph, D and P, where P is some constant n to the minus 1 over k minus 1, then that would contain k power of the Hamiltonian cycle with high probability. Okay, so one thing here is that, again, you can consider construction, the correct unbalanced bipartite graph to show that this threshold on P is actually tight. And this, as I remarked yesterday, okay, so this is for k at least 3. So k minus 1 is at least 2. For k equals to 2, you will need a log factor here. So this n to the 1 minus 1 over k minus 1 is suggestive that it is the threshold for appearance of a k minus 1 power of the Hamiltonian cycle in the random graph. So roughly speaking, here what we are doing is we use the high minimum degree graph G in the background in order to construct some frame so that in the random graph, we only need to find a k minus 1 power instead of a k power. So let's see how that should work. So we will apply the regularity lemma. Now, after we apply the regularity lemma, let's focus on, okay, we can construct what we usually call the reduced graph. So the regularity lemma produce a whole bunch of parts, and then between some pair of parts, the graph is not well controlled. Maybe it's too sparse or it's irregular. So let's ignore these pairs. We will put an edge in the reduced graph across the remaining pairs where the graph in between these pairs is dense and it is regular. So we can check that in this reduced graph, if we put the complete, in this reduced graph, we still have high enough degree because of the high minimum degree condition on the original graph. And then we can show that we can find under this minimum degree condition in the reduced graph a collection of vertex disjoint stars and each of them have at most k leaves. And we can do this for all of the vertex parts, apart from perhaps this small exceptional vertex part that we call V naught, who have size at most something like epsilon n. Okay, covering all but the exceptional vertex part. Of size bigger than epsilon n. Okay, so we extracted out these stars. We can actually just based on the stars that we have produced, which have some uncontrolled number of leaves, have between 1 and k leaves, we can actually subdivide them in some correct way. And then the picture that we have after we clean up is that we can then obtain, apart from, again, this exceptional small vertex part, a collection of vertex disjoint k star And we can also assume that all of the parts have the same sign. Okay. So now with these stars, we can start to see how the stars in the graph G, okay, of course, we apply it to the deterministic graph G. We will see how the graph G allows us to build a frame for the cycle that reduce K to K minus 1 in the remaining part of the cycle that we need to find. So let's look at one of these stars. So let's say K is equal to 3, one of these stars. And this means we have here 4 vertex parts of G, and every of these pair is both dense and epsilon regular. In fact, we can assume that with some standard preprocessing again, we can assume that we have these vertex parts. All of them are dense, epsilon regular, and actually epsilon super regular. So you can also assume here the minimum degree condition. So this is how we are going to find the Hamiltonian cycle, the case power of the Hamiltonian cycle. Well, we'll start from a vertex here, and then we just iteratively go through these parts. So how we want to build a cycle. Okay. Now for every edge of this cycle that goes across this well-controlled pair in a reduced graph, we want to ensure that this edge already come from the graph G, the deterministic graph. So we want to enforce the condition that these red edges in the power of the Hamiltonian cycle I will need some more edges. So we will need that the red edges in the picture come from the graph G. So we then have the remaining edges in the power of the Hamiltonian cycle. So for instance, this edge is not guaranteed to exist in G. At least it doesn't cross between a pair of nice reduced parts. And this edge also do not come between a nice reduced part and this edge. And then we also have this edge. And maybe also this edge. But in proof, you can see that what we have here, in the end, the edges in blue, they will form a 2 power of a Hamiltonian cycle now, instead of a 3 power of a Hamiltonian cycle. And these blue edges are the ones that we will in the end want to find in a random graph. So that's why the threshold we have is corresponding to the threshold for the K minus 1 power of the Hamiltonian cycle. So with that, let me now set it up a little bit more formally. So let's call this star S. So for every star, there is a center. Let's call that Z. There are the leaves, vertices in the leaves of the star. Let's call that W. Well, in the end, we cannot forget completely about this small vertex, exceptional vertex set V0. But what we can do is for each vertex in V0, we can actually assign it appropriately to one of these stars with the condition that that vertex actually have a high degree to the leaf vertices in the star. So we can now redistribute the vertices in V0 into these stars S, and let's call the vertices in V0 that get redistributed here by the name A. So we are going to embed the Hamiltonian cycle, the K power, in some specific way. So roughly, this is what we are going to do. We want to first fix what we call a labeling. So this labeling just tells us, according to what we work on how we work on the cycle, which vertex, the vertex should come from which part in this picture. So there's this part W, this part C, and this part A. So let me first fix how that happens. So maybe here, this is a Z vertex. These X are all of the W vertices. And let's say this is all of S. So we first specify this type of constraints that we want on the embedding of the case power of the Hamiltonian cycle. So what is happening here, we will always alternate. So we always want a Z or an A vertex. And then in between two Z or A vertices, we have a gap that will contain typically exactly K vertices from W. But because some of these additional vertices from A, some of these gaps may have less than K vertices from W, but there will always be some vertex in that gap. And of course, with the parameters that we have, we can always create a labeling, an embedding this way. So now we'll say that an embedding phi from this case power of the Hamiltonian cycle into our graph G, this is good if, well, we have all of the edges that I'm going to draw now in yellow coming from the graph G. So I want all of the edges between a Z vertex and the W vertex in a nearby part. And also the same for the A vertices. Okay, so I want all of these edges to come from G. Okay, let me not maybe draw all of the edges. Okay, so the main lemma that we will use, and it is direct corollary of the random blow-up lemma that we have discussed, is that there exists a good vertex spread distribution over the good embedding. So there exists O1 over N vertex spread distribution over good embedding speed. Okay, under the assumptions that we have on the graph G. So now, after we have this, well, what is our remaining goal? We need to embed the remaining part of the Hamiltonian cycle into the random graph G and P for this correct value of P. So let's let the remaining parts that we need to embed, so let's let H phi be the edges in the cycle subtracted by the edges that we have already forced to be in the graph G. Okay, so this H phi now, under the randomness of the random embedding phi, will give us some distribution of, random, some distribution over subgraphs of the case power of a Hamiltonian cycle. And we want to show that distribution over the subgraph H phi will now have the correct spread property in order for us to obtain that under this probability value of P, the random graph G and P indeed contain with reasonable probability one of these HP, which will then allow us to put the case power into the union of the two graphs. Okay, so now the claim here is that this distribution, okay, maybe I need some more space for the claim. So we'll show that this HP actually has the smooth spread property. For case is 3. So what does this say? So this is essentially the following statement. So for all good embedding P prime, if we look at some subgraph H, which is a subgraph of H of phi prime, with some number h of edges, then, well, our measure vertex distribution, let's call this lambda. The measure lambda over the phi such that h phi intersected with h is having exactly equals to some number t of edges. This is at most the critical value over there, so some constant n to the -1 over k minus 1 raised to the power t. And these are another constraints that t is at least h n to the minus gamma for some constant gamma that may depend on k. Okay, so roughly just the same smooth spread property that we have written down before. And once we show this, then we know that we can run this proof, the Kahn-Kalai conjecture, in constantly many steps and produce that even at a constant factor away from the spread value, n to the -1 over k minus 1, the random graph will contain the graph that we care about, which is h phi. Right, so we apply here the smooth spread lemma of spiral. And okay, so this verification is just some calculation on this fairly explicit graph h phi. So I will not go into the details of the calculation, but one can then do it, and then this would all piece together and show that G and P with high probability contains. So this is roughly the application to perturb random graph that I want to mention. So maybe I'll just conclude by saying that, right, it seems to be a lot happening on this front, and there's been many other arguments as well. So for example, there are very nice arguments of Kelly, Pokrovsky, and Luyesser, and they use the matching lemma in a very different way to produce Hamiltonian cycles in many different contexts, so in hypergraphs, for instance. And the way that they do it there is roughly to say that, well, once we sample random vertex subsets, similar to the application that we discussed on the hypergraph perfect matching, many of the vertex subsets will have the correct minimum degree, but some of them, the exceptional ones, may not. Then they want to then redistribute the vertices in the bad vertex part to the correct places so that we have the correct minimum degree condition, maybe not only within one part, but also between pairs of parts, so that we can start connecting up the Hamiltonian cycle. And the condition that you can write down to where a vertex can be redistributed to, again, you can represent that as a bipartite graph. And then the spread matching lemma allows you to do the redistribution in kind of a maximally spread way. That's another very nice argument. And so there's be a lot more to explore from here, I think. So thank you for your attention.
I have a question. This 1 over k plus 1 is for the star factor. Does it mean that if we, let's say, you just need the almost spanning kk clique, then epsilon linear degree is enough, no?
I see. So what you want to find now is an almost spanning k factor.
Or let's say kth power of almost
Okay,
spanning path.
I
Is
see.
it true that you can lower this 1 over k plus 1 to just epsilon n?
I see. So let me think. Maybe the examples are usually to look at are these unbalanced bipartite graphs. So if you have a very unbalanced complete bipartite graph, then you have to see if you can build. Then I think maybe you can
right.
get almost spanning
Right.
path. like a very short path.
I see.
But I want to say there is indeed really close to kind of a prediction for what should happen in the entire range of delta. So for each maybe specific values of delta, when we saw the picture in the case of the square of a Hamiltonian cycle. And yeah, I forgot to mention the names of the people behind that. So Antonio Dudek, Ryer, Brzezinski, Schad, Butcher, Praxis, Squalia, Clear, and Skoken. So several different works. But yes, that gives a complete picture for the square of a cycle. And for this higher power of the cycle, there might also be some interesting picture regarding the transition in the threshold that you need as the minimum degree of the deterministic part varies. And I think that's something that one can do, one can explore. It mainly would correspond to what kind of structure that one can find in the various different ranges of delta in the reduced graph. And
Okay,
yeah.
Thanks.
In the proving the each side has a smooth spread property, is there some general framework that the vertex spread implies some kind of smooth spread, or this only works for kind of power of Hamilton cycle?
Yeah, so it needs, right, so there's a somewhat general proof that you can write. There are somewhat general and similar calculations that kind of would appear in similar shape in many different places. And I mean, so far it kind of has been verified somewhat more explicitly for these type of structure, like the power of a cycle, just because of the kind of applications that people have looked at. I mean, yeah, I didn't think carefully if there's a very general version of when the vertex spread property implies a smooth spread property, but you use only some quite mild properties of the cycle in order to get this property. And anyway, already just for this graph HV, which is some mild modification of the k-1 power of a cycle, one just need to sit down and then write down the calculation, but it's somewhat annoying. One need to count. Essentially, what you need to do is to control the number of edges in various different types of subgraph of the cycle or this graph HV that you have. And already for HV, it's somewhat annoying. You need to take care of several different types of special vertices. So yeah, I don't know if there's a very general result. At the same time, that sounds something that would be useful.
Thank you.
Do you have any plan to generalize your spread Bloor lemma to spread hypergraph Bloor lemma? That's the curious.
Good question. Maybe there's also some people in the audience who are more of an expert on the hypergraph flow of lemma than I am. I mean, yeah, I don't have a plan to like maybe now do that, but that seems like something that would be nice. And then you would be able to bring hypergraph applications to the robust setting.